Let us in this video today discuss about exactness of first order and first degree linear differential equation. Okay, first order and first degree linear differential equation. What is exactness? What is exactness? The general form for a first order and first degree linear differential equation is dy dx plus p of y equal to q, where this p and q are only functions of x. p, q are function of x only, x only. And this has integrating factor e to the power integral p dx. What is a integrating factor? We must know that integrating factor is a suitable function which makes this differential equation integrable. And what does this term integrable refers to? It refers to that when we multiply with this function, this differential equation, it becomes exact. It becomes exact. Now, exactness is something which is defined as a fact that this differential equation is written as the total differential of a suitable function. That means d of u. The simplest example of this is exactness of a first order and first degree linear differential equation is x dx plus y dy, which gives us d of xy. We may as well take another example, which is y dx minus x dy by x square plus y square. Okay, so this is actually nothing but d of tan inverse y by x. Anyway, let us explain what is meant by this exactness with the general form dy dx plus py equal to q. Let us write the equation and write the integrating factor as e to the power integral p dx. Remember that p is a function of x only. So, from the fundamental theorem of integral calculus, we all know that integral fx dx, p is replaced by fx. Okay, so from fundamental theorem of integral calculus, we all know that integral fx dx is actually nothing but f of x plus some constant c, when dfx dx is equal to fx. Here we have a glimpse of this total differential, since this may be written as this, which is a total differential, and when you integrate both sides we have this. Isn't it so? With this small introduction, let us see that what happens when we multiply with this integrating factor this differential equation. Remember this, that integral fx dx is nothing but fx, and that denotes that f prime x, capital F prime x, is small fx. Okay, so whenever we multiply this with the integrating factor, it becomes e to the power integral p dx into y prime plus py e to the power integral p dx equal to q integral q into e to the power integral p dx. Okay, this is nothing but ddx of y into e to the power integral p dx. So that we may write it as, see, e to the power integral p dx is may as well be written as e to the power capital Fx. Isn't it so? Because we all know that if we replace p by small fx dx, and if we assume that integral fx dx, whenever it is integrable, gives another function of fx. So we replace it with e to the power capital Fx dx, remembering that this is the derivative of it, this is fx. Just remember this. Only then we can replace integral p dx by fx. Now what about this? Whenever we take the derivative of this is dy dx y prime multiplied with e to the power integral p dx plus dy dx, and we keep it fixed, and then we take the derivative of this and keep y fixed, and whenever you take the derivative of e to the power fx, see, this is e to the power capital Fx, so whenever you take the derivative of e to the power capital Fx with respect to x, it gives nothing but this. Isn't it so? And what is f prime x? This is small fx. And what is small fx? We have replaced it by p. So this is equivalent with this. And so this plus this is equivalent to this. Isn't it clear? This term identifies with this, and this term identifies with this. So this is actually ddx of this. And whenever we have ddx of this equal to this, we can easily write that the total differential of this is actually nothing but q e to the power fx dx. And we can integrate both sides to write that actually this is equal to this plus integration constant. It is very interesting to note that whenever we find the integrating factor, we ignore the constant of integration here. Why? Because we are multiplying both sides of the equation with this e to the power integral p dx, which is actually we have assumed that this is nothing but e to the power fx. So if we would have used the integration constant here, it will mark this type of thing, or we may, isn't it so, the constant of integration c, or we may replace it by k, and they cancels out. That doesn't make any difference. So this is a very vital clue which one should remember why we ignore the integration constant in case of integrating factor. And this shows that what is the implication of this integrating factor. By multiplying this differential equation with this integrating factor, we have made it exact. So exactness is equivalent to integrability. Whenever it becomes exact, we can integrate it. So this is the simplest part of the differential equation. And we all know that there is an extension of this simple form of linear differential equation of first order and first degree to the famous Bernoulli equation, which takes the form like this. This is Bernoulli form, which is non-linear actually. N is any number, constant number. Let us assume that n is an integer, and whenever n is greater than 1, this becomes non-linear. Okay, and it's very easy to see that if we divide by y to the power n both sides, it becomes like this, and if we substitute a variable z in place of y this, then dz dx becomes 1 minus n y to the power minus n dy dx. Okay, and this is actually this, so we can replace this with 1 by n dz dx, and this gets back to the previous form, isn't it so? So this is a very simple exercise, and this form is called Bernoulli's equation. But apart from this, we have a bigger class known as nonlinear equation of first order. Okay, and we can take that general form to be m dx plus n dy equal to 0, where we say that this m and n both are function of x and y both. Obviously they are not the same function. If we denote m to be the fxy, they may be same or may not be same. For the sake of generalization, we should write like this, that m is some function of x and y both, and n is some other function. Okay, now the point is that this is no longer linear, because it can be any function of x. As for example, it can be like this. Okay, it can as well be like this, dx y to the power minus 2 plus x to the power minus 2 dy, and a plethora of forms. We have written some arbitrary forms like this. Now let us discuss about the exactness of this m dx plus n dy form, which may be non-linear in a sense that it will be any function of x and y. So m dx plus n dy is exact only when we have del m del y is equal to del n del x. Okay, the partial derivative of this function m with respect to y is equal to the partial derivative of n with respect to x. We all know about the partial derivative, I hope. Any function of two variables x and y. So del m del y is nothing but original derivative dm dy when x is kept constant. And similarly in case of n, which is another function of both x and y, where x and y are both treated to be independent variable, then del n del x indicates actually dn dx, getting the derivative of n where y is treated to be constant. And similarly del m del y is a dm dy treating x constant. Whenever we have del m del y equal to del n del x, this m dx plus n dy format is exact. And this is an if and only if condition. Why? Let us discuss this. This is exact whenever this if and only if condition, del m del y is equal to del n del x. That means whenever this is exact, we have this, and whenever we have this will be exact. So this is very easy if you consider that any function u x y, its total derivative, where x and y are both treated as independent variable, may be written as del u del x into dx plus del u del y into dy, simply because of the linearity condition. Because del u del x is the rate of change of this variable with respect to x only, and we have multiplied it with dx, and del u del y is the rate of change of uxy with respect to y only, and we have multiplied it with dy. So the total differential of this function uxy is equal to del u del x dx plus del u del y dy. This stems from the theory of differential calculus of two variables. This is to be accepted, and if we accept this and compare this with this, we see that m is del u del x and n is del u del y. So we have del m del y as del y of del u del x, which may easily be written as del x of del u del y, simply because u is a continuous function of xy. Whenever u is not a continuous function, we cannot write this, and whenever u is a continuous function, we can flip them. The order of the integration is commutative, and we have this equal to del n del x. So whenever this is exact, that means we can express this as a total differential. We have this, and whenever we have this, we obviously have this, because whenever del m del y equal to del n del x, we have del 2y del x2 equal to this, and we can express the function u as this, which gives that m is identified with del u del x and n is identified with del u del y, which makes this as an exact equation. We can as well see that whenever del m del y equal to del n del x, if we integrate, they will give us an exact equation. Isn't it so? Whenever this is an exact equation, it can be expressed as a total differential. For the clarity of this, one must have to acquire an idea about partial derivative, what partial derivative is all about.